Good morning. Today what we're going to do is talk about the laws of logs. This is section 8.3 Pre-Calc 30. We've spent a little bit of time talking about what a logarithm is. We've talked a little bit about the graph of logarithms, of logarithm functions. But today what we're going to do is move forward in terms of how we're going to learn how to solve logarithmic equations. And these laws of logs are going to help us with simplifying equations to get them ready for solving, which we'll do in section 8.4. So there's a couple of things that we're going to start off with, some examples to develop our laws of logs. These three examples that we're going to start with today are asking us to take a look at some ways of manipulating, multiplying, dividing, those kinds of things with logarithms, what we can and cannot do. So this first question is asking us to use a calculator, and you'll notice that all of these questions, all of these logarithms are base 10. I don't see any little base written with the logarithm, so we assume it's a base 10, a common log, but they're all very easy to put into our calculator. So what they're asking us to do is to find to 4 decimal places with a calculator approximately what log of 6 plus log of 5 is. And so log of 6, you watch with your brackets, we want to close that bracket off, plus log of 5 ends up being a number that is 1.4771 to 1 decimal place. There's one other expression in this part that has the same value. And if you go through all of them, you will find that log of 30 has exactly the same value. And now what our goal is in this first question is to match up to see which ones have the same value. So this adding of log of 6 and log of 5 is going to give you the same value as log of 30, which has the same approximate value. And if you go through these and match them up, you're going to find that log of 11 plus log of 9 is equivalent to log of 99. You're going to find that log of 7 plus log of 3 is equivalent to log of 21. So what's the connection between these is really what we're trying to find out, because each of these 3 examples here have 2 logarithm expressions being added together, whereas these 3 have a single log expression and only one thing that you're taking the logarithm of. So what's the connection between the ones that give you the same equivalent value? And if you go through and you look at some patterns, you're going to notice that there is a connection when you have 2 log expressions, and it doesn't matter what the base is, you're going to find the same equivalent value is if you were to multiply these 2 pieces together, what we're taking the logarithm of, that it works out equivalent. So the log of 7 plus log of 3, 7 times 3 is 21, and that gives us the same numerical value. That's our first law of logarithms that's going to help us out. It's a way of either A, writing 2 log expressions into a 1, simplifying it down to 1, or taking a single log expression and maybe being able to separate it into 2 logs. So same idea in number 2 here, asking us to use the calculator to find the approximate values. There's a connection between these 6. Again, if you take some time to go through and evaluate them to 4 decimal places, you're going to find, for example, that these 2, log of 12 and log of 48, now minus log of 4, are equivalent. You're going to notice that these 2, log of 35 minus log of 5 is equivalent to log of 7, and these 2 are equivalent. What you may notice again between the ones that are connected or equivalent, that these 2 logarithm terms, when simplified, are equivalent to this single log. So what's the connection between the numbers that we see? They all have that base 10. What you will notice is that if you have two log expressions being subtracted, that they are going to be the equivalent of a single log, but the two expressions are being divided. The first one is on the top, the second one that was being subtracted is on the bottom, and what we have is a second law of logs. Third one down at the bottom here, again, these ones are all one log term. They're not multiple terms, but some of them have a number in the front multiplied to the logarithm expression. And so if you were to go through and again use your calculator to find their value to 4 decimal places, what you would notice that these two are equivalent. You would notice that these two are equivalent, and these two are equivalent. So again, what's the pattern? What connects 3 log of 5 to log of 125? And if you go through them, you will find that if you have a number multiplied in front of a log expression, that would be equivalent to a log of that same expression, but now with an exponent of a. So that number that multiplies out the front comes up and acts as an exponent on our expression. And we have 3 laws of logs that we are going to practice today. So when you take a look at the next part of the notes here, they review those laws of logs. The product law, again, as I said, multiplying 2 expressions together can be rewritten as 2 individual logs, but added together. As long as the base is the same, and they use C to indicate that the base is the same, the quotient law and the power law. So all of those are things that we're going to practice today. So I've got a few examples that I've picked out to go through with you. In this first example, they're asking us to write each expression in terms of individual logarithms of x, y, and z. That means that each of these variables are going to have their own log expression. So we're going to have multiple log expressions. We're starting with a single log, and they're wanting us to break this down so that the x and y have their own log term. So because these two are dividing, x divided by y, it makes me think of my quotient rule, and so I can rewrite it in this pattern where I have log terms subtracted from each other. So it would be rewritten as log in base 6. The top one, x, is part of our first term, minus log 6 of y, which is the denominator. Now, because we have variables, we're not evaluating these. We're not getting it down to a numerical answer, but it's just another way of writing it. And so it's an equivalent expression, just with multiple log terms rather than a single. D is my next one that I'm going to do here. This one here has 3 variables, x to the power of 5, y, and all being divided by the square root of z. So we have 2 terms that are multiplied together on the top. Using that product rule, I'm going to write it as a sum of terms. So log in base 7 is what we're starting with. The x to the power of 5 was first. I'm going to add that on to log in base 7 still of the y. The term that is being divided, the square root of z, is going to come after a subtraction sign, log still in base 7 of the square root of z. Now, that technically satisfies the instructions. I have 3 individual terms, their own logs with each variable by itself, but you may notice that they may take these 2 terms a step further. For example, with the x to the power of 5, with this logarithm, I could use the power rule. You may see the answer with the 5 move down in front and multiplied to log of x in base 7. Similarly, not the second term, but the third term, if I wanted to do that same pattern here, the square root of z is not a power, not now, but I would need to rewrite it as a power of a half if I wanted to take it one step further so that this log expression doesn't have a power. Just rewriting the first two terms. I'm not doing anything with those. But the 1/2 could come and multiply out the front of this log expression, and then the z would be the only variable there. Sometimes we want to have a simplified variable, just simply if we're wanting to solve, we'd rather have a z than a square root of z or a z to the power of a half. Those ones all involve variables. This example here is wanting us to use those laws of logs to simplify and evaluate. So we're going to simplify it first, then we'll evaluate it to get to a numerical answer. So for the first one, in part A, this is log in base 3 of 9 times the square root of 3. I'm going to avoid using my calculator. I'm going to see if I can evaluate this simply because this 9 square root of 3, these are all 3s. This is all broken down to 3s and it's base 3, so I can see some values that would make it easy to figure out without a calculator. But how do I go about doing that? Well, first of all, I do see two expressions, two values multiplied together here. That makes me think of my product rule. My product rule, I have things multiplied together. I'm going to rewrite it as a sum of terms. So the first step that I'm going to do is take the 9 and attach it to its own log, and then the square root of 3 with its own log. Now, how does that make it easier to evaluate? I'm going to do the evaluating in a second, but we have to remember what logarithms mean. For example, this first term here, log of 9 in base 3, when I see that term, what I'm thinking is this: 3 to what power is equal to 9? We've spent some time converting logarithms to exponential form and back and forth. And so when I think of it as an exponent, I can see very quickly that I would be needing a power of 2 on a 3 to make it equivalent to 9. And that's really what this is asking, is what's the missing exponent? So I could evaluate this first piece to 2, because it was 2 that was the missing exponent. Now with the second term, it may not be quite as simple yet. So what I'm going to do is I'm going to rewrite the square root as a power of a half. Now that's not bad. I haven't done any simplifying really, but I do know about my power rule that would allow me to move that power of a half down the front. The 2 I'm done with. 1/2 out the front of log of 3 in base 3. Now again, this piece right here, when I think of it as an exponent, base 3, to what exponent is going to give me this answer of 3? So for this piece of the expression, log of 3 in base 3, we're looking for the missing exponent, which would be a 1 to make it equivalent. So if I were to rewrite this, it would be log of 3 in base 3 is equivalent to 1. 2 plus a half, that's multiplied by 1, is still a half. And I would have 2 1/2 or 5/2. So for part A, rewriting it as separate logs allowed me to evaluate each log independently, simplify it down to a numerical value, and I can simplify the expression without having to use a calculator. All right, I've got one more circled here. Hopefully I have enough room to do this one. I have a 2 multiplied out the front, a half multiplied out the front of this log expression. I'm going to simplify this. There's a couple of things I want to do first. I cannot use the product or the quotient rule. So let's make sure that this is clear. I cannot use the product or the quotient rule when I have numbers out the front. The only way I can use the product or the quotient rule is when it is a log with some expression. So my first job in part C here would be to move the 2 up and make it an exponent. Same thing with a half. I can't do anything until I move that up and make it an exponent. The third log expression didn't have a number up the front, so it was fine. Now, with these powers, I can actually finish simplifying this individual term before I do anything. 6 squared is 36. 64 to the power of a half is like the square root of 64, which is 8. All right, so now I have 3 log expressions. I've done some simplifying, some working with it, but I'm not at a point where I can evaluate it. When I did part A, 3s and 9s, 3s and square root of 3s, they all were a common base of 3. Whereas this base of 3 with 36 or 3 with 8, these are not numbers that are nice. I call them perfects, not the way that they are written. So I cannot evaluate them individually. What I am going to do with this one is I'm actually going to put it back as to a single term. That first example that I did was a single term, and I broke it apart. It seemed fitting at the time. This one has separate logs, but I'm not seeing how I can evaluate them. And so what I'm going to do is I'm going to rewrite it as a single log. These 2 terms are being subtracted. That means the 36 is going to divide by 8. Well, we know 36 doesn't divide nicely by 8, but this term that is being added on is being multiplied. So rewriting it as a single log, 36 divided by 8 times 2, that is the expression. Based on the subtracting, turns it into a dividing. The adding of terms turns it into a multiplication. When you look at the numerical value that we have here, simplifying this in whatever way, 36 times 2 is 72, divided by 8 is equivalent to 9. Now this is much easier for us to evaluate, because when I look at this log of 9 in base 3, when I think of it as an exponent, we're back to something that we just did. That's really asking us 3 to what power is going to give you 9, and we already know that 3 squared is going to give you an answer of 9. So we were able to evaluate this expression using our laws of logs and what we understand about exponents to figure out a simplified answer. So using laws of logs in one way or other, having a single log, rewriting it as 2 separate log terms, having 2 separate log terms, writing it as a single log, it really depends on the question as to what is going to be the better route to go. One more example here, writing each expression as a single logarithm in simplest form, which is similar to what we've already kind of been working with. But this has an extra element. It's asking us to state the restrictions on the variables. The 2 examples that we have here have variables, x's, throughout the question, and there are restrictions on those variables. I'm going to flip over so that we can take a look at that, see what they're asking us to do with a focus on the restriction part. The first example, log 4 times log of x in base 3 minus, now there's a half written out the front of this expression, and so they're asking us to simplify it down to a single log. That was the first instruction. The restrictions was the second part. So there's a couple of issues with this. Again, I cannot use the product or the quotient rules until these numbers that are out the front are moved up. So for the first term, that power of 4, that 4 that's being multiplied is going to come up and become a power of 4. I can't do that quite yet with this one. The half is being multiplied to the bracket. So what I feel I need to do first is distribute that half to both terms oh, that should be a minus sign now. The half being multiplied to the 5, negative 5 halves. And we have that 5 halves being multiplied to log of x in base 3. All the same bases, which is really important for using those laws of logs. Now, when it comes to the next step, again, I can't do anything with the product or the quotient rules until these numbers are moved up as a power. So I've got another step to go here. Moving the half up to make it an exponent on the x. Moving the 5 halves up and making it an exponent on the x. So now when I take a look at this, 3 individual log terms, no numbers multiplied out the front. I can simplify this using the quotient rule. I see a bunch of subtracting signs, which means that when I go to write it as a single log in base 3, the x to the power of 4, and I guess you can think of it this way, there's like a positive sign out the front, so that automatically makes it go on the top. The minus sign says that we're going to divide this x to the power of a half, and another minus sign, which means again we're dividing. So it's going to go in the bottom, dividing that x to the power of 5. And so we now have a single log with a single expression, but it's kind of a mess. I wouldn't say that that would be simplified as much as I can because I have something that I can simplify. These are using or exponents, powers on each of these like bases, the same base. So I'm just going to use some of those rules, those exponent laws now. There's exponent laws, there's laws of logs. But exponent rules, for example, the bottom that says when you are multiplying like bases, we add our exponents. So a half plus 5 halves, nice fractions there, is going to be 6 halves. 6 over 2, which is the same thing as 3. One more step. When I am dividing like bases, subtracting the exponents becomes x to the power of 1. That is my simplified answer as much as possible using my laws of logs and a few exponent laws to go in with it. Now, part of the question was asking us to take the original expression and simplify it down to a single log, much simpler, definitely. But it was also asking us about restrictions. And earlier on in chapter 8, we talked about certain limitations when we had logarithm expressions. You may remember that our bases were positive numbers. And for that reason, when you look at something like log of x in base 3, if I were to think of this with converting it to exponent form, what we're talking about is 3 to some power is going to equal x. Now we can have any kind of exponent that we want, positive or negative exponent, but the answer of this exponential form of the equation, if you are multiplying a bunch of 3's, a bunch of positive 3's together, the answer you get is never going to be a negative answer. It's never going to be equal to 0. This x value, when you take a look at the expression we're taking the logarithm of, it can only ever be a positive answer. So any logarithm expression that we are working with always has to have a positive expression. Now with x, we don't know what x represents, but we can say that within a restriction that we do know that x is going to have to be greater than 0. So the restrictions, whether you were looking at the beginning or at the end, the restrictions are going to be the same. Which is why with the second example here, I'm not going to go through the process of simplifying it for right now. I'll do that for my notes. I want to focus on the restrictions part of this question so that you can see why the restrictions are what they are for something that looks like this. Because these expressions, log of x squared minus 9 in base 2, is a little more complicated than just a simple x. But the premise still stays the same, that that expression has to be greater than 0. It has to be positive. So how do we decide what values of x that we can put in here are going to make this expression, x squared minus 9, greater than 0. This kind of looks like a quadratic equation. We've solved quadratic equations in the past. It's not really an equation, it's an inequation. But we're going to use some similar elements. For example, the fact that x squared minus 9 can be factored. It is the difference of two squares. Now, when you go to multiply these factors together, if we want to keep it greater than 0, positive, well, how do we multiply things and get a positive answer? Well, either these two expressions, these two factors have to both be positive. A positive times a positive will be a positive overall, or they both have to be negative. A negative times a negative is going to still be positive overall. So when we take a look at determining the restrictions for this particular logarithm piece of the question, we are going to have to decide x minus 3 is going to have to be positive, and x plus 3 has to be positive. Well, what that means is that when I move the 3 to the other side, I add 3. X has to be greater than 3, and x has to be greater than, when I move the 3 over, negative 3. That takes care of when they are both positive. I'm just going to do this. Or the x minus 3 has to be negative, less than 0, and the x plus 3 has to be less than 0. So we would have x is less than positive 3, and x is less than negative 3. We've got two ways that we can take a look at our overall expression, x squared minus 9, being greater than 0. Now we have a little bit of some overlap here. There's x is greater than 3, but x is less than 3. X is greater than negative 3, x is less than negative 3. It's hard to get some sense out of what could all of these possibilities be narrowed down to. So when we take a look at the other expression as well, we would have to go through the same process of factoring the x squared minus x minus 6 and sort out what kind of values that we could be taking a look at. So I'm just going to do that over here. I'm going to write this again, restrictions. The x squared minus x minus 6 has to be greater than 0. This is also factorable. So when you look at factoring x squared minus x minus 6, we're talking about x minus 3 and x plus 2 are the factors that would multiply to negative 6 and add up to negative 1. So again, we're at a situation here where these two factors, if they happen to both be positive, would still be positive overall and greater than 0, or they have to both be negative. So it looks similar to what I did over here. I'm just going to do that again. X minus 3 is greater than 0, and x plus 2 is greater than 0. So that means that x is greater than 3, and x is greater than negative 2 is one situation where they were both the positives. Or we have the x minus 3 is less than 0, and x plus 2 is less than 0. So x is less than 3, and x is less than negative 2. We've got quite a few different inequalities here now. So how do we narrow down to our restrictions? This last question was much easier. It was very straightforward. We had one expression. It was linear, power of 1. So we didn't have all of this factoring and stuff going on. So what kind of values out of all of the ones that we have here that we've got listed are going to be situations where we are going to have values that are going to keep these log expressions greater than 0? Some commonalities here. We have greater than 3s. We have less than 3s. We have greater than negative 2s, less than negative 2, so we've got numbers all over the place. So which of these are going to be the ones that are going to hold true? Okay? So I guess that it would come down to trying to sort through some numerical values and just test them, I guess, to see which ones are going to make the most sense. So for example, if I have numbers that are greater than 3, like 4 or 5, if I were to put them in these expressions, would they stay positive? Okay. We have things like less than negative 3, less than negative 2. So when we talk about extremes, I guess is what I'm looking for, greater than 3, greater than negative 2. Well, greater than 3, if something is greater than 3, it's automatically going to be greater than negative 2. So in terms of this, I see x being greater than 3 is going to be kind of on the high end. Again, if you were to try numbers that are greater than 3, like 4s and 5s and 6s, they would keep those expressions positive. Now when we've got some less thans, extremes again, I see less than 3, but negative 2 is smaller. Anything less than negative 2 would definitely be less than negative 3. But over here we had less than negative 3. So the extremes in these cases here, if it's less than 3, if it's less than negative 3, well, if it's less than negative 3, then it would have to be less than negative 3 or less than positive 3 overall. So again, if you were to try numbers that are less than negative 3, like negative 4, negative 5, negative 6, these would keep these expressions positive. So when it comes to our restrictions, these two scenarios are what we are looking for. That we have greater than 3 or less than negative 3. Those are the only values that would keep this equation correct. So what I'm going to do is I'll finish up this simplifying of this expression. It's very similar to some of the other ones that we've done, but the restrictions part was something that was a little bit more involved for this particular question. I wanted to focus on that. So for those of you that are ready to get started, page 400, 1 to 3, 10, 11, and 15 will give you some practice with working with your laws of exponents. Thanks. Have a good day.